Okay, so part 4 is about how Bayesian inference can contribute to problems that are genuinely difficult, that right now we would not be able to solve with convex or non-convex optimization, and where really the whole history of sparsity and regularizing and all of that is really insufficient to address the problem. Okay, so before I can tell you that, I'll tell you about skin, because rather than introducing all these modeling strategies and difficulties in an abstract setting, I decided to introduce them through a sort of like running example, an application that I studied a few years ago, and where all these ingredients come in. Okay, so this application will involve finding tumors in skin tissue, so skin melanoma tumors. So I'll be talking a bit about skin. And what you need to know is that our skin has some layers. The outer layer is called epidermis. Then there is a layer called dermis, which is subdivided into reticular dermis, and I don't even remember anymore how the other part of the papillary dermis and reticular dermis, and then subcutaneous fat, the hypodermis. And melanoma tumors tend to live here, near the surface. They grow at this intersection. You see them on the epidermis, and they start going down. And as long as they are here in the dermis, then you're safe, because there is no blood supply. But when they get really low here, they start getting a lot of blood supply. And when they get blood supply, they can grow, and their metabolism increases, and then you die, basically. The melanoma tumors are very deadly, so if you're in that situation, then you're in trouble. So how do we treat them? Well, they are resistant to radiotherapy and to chemotherapy and to pretty much everything we can throw at them, except for some experimental treatments. So what we do is we remove them. They're close at the surface, so we remove them. But when we remove them, we have a number of problems. We might not completely remove the tumor, and then the patient still has cancer. Or we might remove it successfully, but have created a wound that then gets infected, and the patient has complications from the infection. Or it might simply be that the lesion is here, and then you end up with a scar that is unpleasant. So we want to do this in a way that is as careful as possible. So what we do in practice is that we remove the lesion with some margins to have a bit of safety. But then we have to analyze what we remove to check that all the tumor is within the margins. And quite often it is not, and the patient needs to come back, and then we remove a bit more, and we retest. Sometimes they need to come 3 times. And this is, this generates trauma. So we would like to remove just once and make sure we remove all that we need to remove without unnecessarily removing too much tissue to minimize other complications such as infections. So there's a new imaging modality to do this called high-frequency ultrasound imaging, and it's ultrasound imaging like what you would use to assess the heart or a fetal scan, but at very, very high frequency. And that very, very high frequency allows you to observe the skin, which is something we couldn't do, 10 years ago. And we can do it in 3D. So we get a 3D image of the skin. Here I'm just showing one slice. And what you observe is this bright line. This is the epidermis, and then what starts is the dermis. And this is fat tissue. So the interesting part of the image is this. And although you can't see it very well because we have 3D scans, but we don't have projectors with good contrast yet, is that there's a dark spot here. That dark spot is a melanoma tumor. Because there's a melanoma tumor, then what we want to do in this image is to decide how deep the melanoma tumor is. And once we know how deep it is, we know how much we need to take out. There's lots of rules that you do the prognosis. So when you have a patient, you can tell if it's stage 1, 2, 3, or 4, based on how deep the tumor is going, and how much access to blood vessels it has had, and how complicated it is. So you know, you decide how you're going to treat the patient based on that. So the plan is, can we use this image to get a good feel for the depth? When dermatologists assess the boundaries of the tumor, they don't do it very well because it's a very difficult task. This image is full of a multiplicative noise called speckle that makes it difficult. And then if it's a 3D image, finding the boundaries of the tumor in 3D is very time consuming. It takes many hours, so unless you do it very quickly. But in any case, it would be good to have an automatic method to do this. So what we want to do is do this in a way that is automatic and reliable, so that we don't have to depend on experts who don't necessarily agree with each other and that have to spend a lot of their time doing this task. So doing this with a non-Bayesian method would be very difficult for reasons that I'll make clear very soon. So what we'll do is we'll throw the full Bayesian machinery at this and see what we can propose. So the first thing we need to know is what's the model for this kind of image. So we said that we'll have something that looks like P of y given x, and then P of x. So the first part is what's P of y given x in this case. We have multiplicative noise, so clearly a Gaussian likelihood, like a squared data fidelity term, L2, will not work at all. You can try it, it doesn't work at all. We need to have a really good model that really captures, the subtleties of this image. So we'll use physics. And I like this example of Bayesian modeling because I think it highlights some of the limitations of machine learning approaches and the advantages of Bayesian modeling in some cases. So in this case, we could try to learn this from data. But this is a new imaging modality. There's not a lot of data. So learning it would be difficult. And we can only really get a good model at this stage by using human intelligence as opposed to artificial intelligence. So we go to a physics book and we see, well, what is this signal that I'm observing? How does it generate? How does it arise? So what we see is that sort of like a simple first order model says that there is a pulse of ultrasound that goes into the skin and starts bouncing back with all of the objects that reflect pulses. So this would be true for ultrasound in any medium, not skin. So if ultrasound travels through water and encounters bubbles, it will bounce back. And it will bounce back to this sensor, and at the sensor what you will record is the sum of the superposition of lots of pulses, m, if there are m bubbles, or what we call scatterers, and they are delayed by a phase that depends on how far the bubble is from the sensor, and they are attenuated by some coefficient a1, ai that depends on how big the bubble is, essentially, or how much it reflects the signal, so how reflective my scatterer is. We don't use this signal directly to construct the ultrasound image. We construct what we call a B-scan mode. So what we take is the envelope of that. We take that signal and we do something called the Hilbert transform of that, and then we do the sum of the absolute value of this. And what you get is basically like an envelope detection. So it's like demodulating a high-frequency signal. The key point is this is something that has zero mean, and this is something that is always positive, and it tells you how big your signal is after filtering out oscillations in the signal that come from the pulse. So it's good for knowing how large AI is, or the sum of the AIs is. Okay, the problem is that M, A, and tau, the delays, the amplitudes, and the number of scatterers are all unknown in imaging. So we'll need to do something to start to learn about these values. So given this physical model, what distribution should my signal have? So the standard answer to this is that this signal should have a Gaussian distribution, and this signal, the envelope, should have a Rayleigh distribution, which is what you get by taking a Gaussian sequence and applying this transform. the Gaussian signal has zero mean, but its variance is not constant. It depends on the model, and it's not known. And the Rayleigh distribution depends only on the variance. And this variance is proportional to the number of scatterers and the average value of the second moment of the scatterers. So if you have scatterers that on average are very large, or you have many scatterers, then you'll get a lot of power back. And this variance will be large, and you'll see this as a bright spot if you look at this signal. And if you don't have a lot, then this will be small, and you won't have a lot of power back. Okay, so that's what we're seeing in this image, is regions of large power, and regions of low power, and regions where there's a lot of intermediate values that look very noisy. And that's why it looks this way. There's multiplicative noise, because our signal has mean 0 and have some unstable variance that depends on the pixel. Okay. Is this a good model? No. This is a good model, but this analysis that it's Gaussian is not good. So where does this analysis come from? It comes from supposing that the number of scatterers is very large and letting a central limit theorem kick in. So then each one of these ones behaves like a random variable, and when you do the sum of a lot of this, if you normalize it a bit, you get a Gaussian random variable. And if you transform a Gaussian, you get a Rayleigh. Okay. But when you do an empirical histogram and you compare this to some fits, you don't get something that is Rayleigh at all. And if you did it on the other signal, it would not look Gaussian at all. So people have worked on generalizations. So these three are generalizations of Rayleigh that include Rayleigh as a special case. So if Rayleigh was the solution, the three would coincide and it would match. And they have come up with solutions that match a bit what's happening here, but clearly they don't match what's happening in the tails. So here I'm showing the histogram in a logarithmic scale to highlight what happens in the tails. So my empirical observations don't fall at all on what my model predicts, and they don't fall too much on what the generalizations of my model predict. And the reason for this is that these generalizations are empirical guesses. People have thought, well, if it's not Rayleigh, then it could be something else. And maybe it's because the number of scatterers is very low. So in, I don't know, underwater radar, the number of scatterers is sometimes a bit low. So they get things that are not Rayleigh, not Gaussian. And then they go, what could it be? Well, maybe it could be Nakagami or generalized gamma or Weibull. These are things that have analytic expressions. So I can postulate that model and use it. And if it fits, it fits. So it's like an operational approximation. But it's not working in skin. So how come that this is not Gaussian? So what we did here is, as opposed to trying to come up with another empirical approximation, which was clearly something people had tried in the literature and was not successful, we did some math, which is what I think you would do, given your background, at least most of you. So we said, well, why don't we do a mathematical analysis of what's going on and see if the math suggests an alternative. So, well, why would this be not Gaussian? Well, if M is not large enough, then we don't have a central limit theorem. Okay. For skin, that doesn't sound like a good candidate, because skin is full of structures, and they will reflect ultrasound. So skin is probably full of scatterers. The other idea is that, well, the central limit theorem likes for random variables to be equally distributed. So if they're very uneven, or particularly their variance is very large, this can delay the central limit theorem. So even if you have a lot of variables, if their variance is very large and their distribution is very no Gaussian, it can take a long time for the central limit theorem to bring it to a Gaussian. So that could be an idea. And then maybe the signal formation model is poor. But this is a physical model that people have used a lot in lots of applications. And although it's not perfect, it seems to be working quite well in every other medium other than skin. So let's focus on this one. Let's assume that maybe this has very high variance and that it's fluctuating a bit, and maybe that's why it's not working. So if M is large, but this is not working, then what distributions could we have that are not Gaussian with M infinitely large? is the Gaussian the only thing that has a central limit theorem? Well, it turns out no. The Gaussian is not the only distribution that has a central limit theorem. The Gaussian is the only distribution that has a central limit theorem with those three hypotheses: IID, finite variance, and independence, which you can relax a bit. If you have something that is a bit different, you could end up in a different limit distribution as n goes to infinity. So to understand that, you need to understand what are the distributions that have what we call domains of attraction. So if I take many distributions and I random variables and I'll sum them, their distribution converges to a Gaussian because it is in the domain of attraction of the Gaussian. Maybe there are others that have domains of attraction, and there are others that have domains of attraction. So maybe it could be in the domain of attraction of a different one, which is not the Gaussian. So let's look at what other domains we have. It turns out there are infinitely other domains, but we can put them all in a single family. So I'll talk about three main results. The first result is, well, if it has non-Gaussian distributions, then we know from the probability literature that it has to be an alpha stable limiting distribution. So that's the class that includes the Gaussian. Because our signals are zero mean, it has to be what we call a symmetric alpha stable distribution. So if it is converging because there is a central limit, but it's not the Gaussian central limit theorem, then it has to be a symmetric alpha stable. And it has a parameter alpha that goes between 0 and 2. When alpha is equal to 2, it's Gaussian. If it's more than 2, it's not Gaussian. And gamma just controls the scale or the power of the signal, if you want. The second thing we'll show is that if this holds, then it means that the scatterers have a distribution that is heavy-tailed, something like a power law distribution. And power law distributions don't have a variance. So if the distribution of the AIs doesn't have a variance, because the tail is too heavy, then naturally the central limit theorem will not kick in, because you're outside the domain of attraction and you'll converge to something else. And you'll converge to a power law with an exponent alpha that is the same that you have here. And the envelope, so the signal that I will actually measure, will have this distribution called alpha Rayleigh. So how do we go about this? Well, if as m goes to infinity, the number of scatterers goes to infinity, my distribution of the sum converges, then it means that my distribution is invariant to addition, because after I've added a certain number of random variables, the distribution does not change anymore. Otherwise, there is no limit. So, well, if it's invariant to addition, then it has to be one of these symmetric alpha stables, because invariance to addition means that the characteristic function must be closed under exponentiation, and only the alpha stable have this property. And because this is statistically symmetric, then it has to be this specific alpha stable called symmetric alpha stable. And if alpha was 2 or larger than 2, then we would be in the Gaussian case. But we're not. So we are in a case that is non-Gaussian, and alpha is between 0 and 2. Great. So what does this tell us about the scatterers? Well, we know from some I think these are two Russian probabilists, but maybe they're from another ex-Soviet country, that the signal is in the domain of attraction of the symmetric alpha stables only if it verifies some conditions on capital F, the cumulative density function. And by playing a bit with this, it's easy to show that this only happens if this product of the pulse signal and the scatterer has a power law distribution. So instead of being exponential of minus something, it is absolute value to some negative power. So it's a polynomial tail and not an exponential tail. And it's not difficult to show that if that product is having, so instead this product has a power law distribution, because U, the pulse, is not something that could have a power law distribution, then it has to come from the fact that the scatterers have a power law distribution. So how can this happen? Well, if I take, for instance, a random network, which is a reasonable model for the skin collagen fibers in the skin, so the collagen fibers that compose most of the dermis, then when you take a cross-section of this, you can show that a cross-section will have a power law distribution. And yeah, so if your ultrasound signal is essentially bounding on the collagen fibers, for instance, then you'll get an amount of energy back that follows a power law distribution. So the AIs will be power law. It will be some function that it doesn't matter that controls what happens at 0, and then a tail that is polynomial. And this will make your signal look something that has infinite variance, and then you will not converge to the Gaussian central limit theorem. Okay, fine. And instead, you'll have an envelope that follows an alpha-Rayleigh distribution. And the alpha-Rayleigh distribution is problematic for many reasons. It doesn't have a closed form expression. The expression is an integral, which depends on a Bessel function. So it's a nasty expression. And this is our data fidelity term. Our data fidelity term for Rn makes Rn appear here inside the Bessel function and here multiplying. So we'll have a data fidelity term that is not at all like a quadratic data fidelity term. If you look at how this behaves, it is very not convex. So this is not something that I could then optimize with respect to Rn or anything like that. And what I care about is, Rn will be observed, and what I care about are alpha and beta, and alpha appears here inside the exponential. So this is a complicated function to evaluate. Okay, so for modeling purposes, to make sense of this signal, it's enough to work with this model. And what it tells you is that the scale of the signal you observe is directly related to the number of scatterers and the number of and their size, so like in the Gaussian model, but in a slightly different way. And now you have a model for your signal that you derived from physics and a bit of mathematics. The question is, does it fit the data well? Well, luckily, yes, it does. Otherwise, I would have lost a big part of my research time. So it does. It fits really well. So this is the empirical distribution, and in red is the new model we proposed, and it fits nicely. And if we go to the logarithmic scale, we see that it captures the tail perfectly well. So you see, with a bit of math and physics, you can get very far. Much better than guessing models or trying to let your computer figure out what's the model you should be using. When you don't have a lot of data, the computer might not do a good job. Your brain will do a brilliant job. So now we have a data fidelity term. So now I want to start identifying the different tissues in the image. And what my model says is that each tissue will have one of these distributions. It's not telling me what distribution it will be. It's saying, depending on the number of scatterers and their properties in each tissue, you'll have a different alpha and beta, so you'll have a different model. But it's not telling you what those values will be. You have to find out that from the data. So let's talk about a Bayesian model to do that. Well, the first thing we need to do is come up with a model for a biological tissue that we're going to split into different classes. So let's say this is my image. I'm going to say, well, this is maybe region 1, and this is maybe region 2, and maybe this is region 3, and then this is region 4. I don't know. So I'll postulate that I have k different classes of or tissues in my image, and each class will be associated with a value that goes from 1 to capital K, and then each pixel or voxel in 3D will have a label. So we have n pixels or voxels in 3D, and then we'll have n labels. And these labels will map each pixel to a class. They'll say, this is dermis, this is hypodermis, this is epidermis. And what this is saying is that if pixel n belongs to class K, then that voxel comes from this distribution, the alpha-Rayleigh distribution with parameters alpha k and gamma k. So your choice of the tissue or the class determines the parameters of the distribution you are going to use as data fidelity term for R. So what you see is that you have, for each class, a different data fidelity term for that pixel. And you'll have to ask the model to figure out what's the data fidelity term that goes in that pixel. So you are entertaining k possible data fidelity terms for each pixel. You'll have to choose, and an additional complication is that you don't know the values of alpha k and gamma k that you should use, and you'll have to find those at the same time. So the alpha k and the gamma k are unknown, so what you try to do is compute a maximum-a-posteriori estimation for the labels, so do a segmentation of the image, find out what is the best model for each pixel, if it's tissue, epidermis, hypodermis, reticular dermis, or papillary dermis, or tumor. After you have marginalized all possible values for gamma k and alpha k. Because these ones are unknown, and you have to get rid of them, just like I got rid of the realization parameter a bit earlier. Okay, so the data fidelity term, as I said, is the alpha-Rayleigh model. I want to write it down for the whole image, so I need to write down a product of many of these alpha-Rayleigh models, one per pixel. And that gives you the whole likelihood for the whole image. And this is if you know the labels. And now I have to put priors on this, because the problem is too ill-conditional. There's no hope I could estimate the alpha k, the gamma k, and the labels from the image if I didn't impose some regularity. What I'm going to do is I'm going to use a Potts-Markov random field to promote regularity. And Daniel Kramer already talked about this kind of model for segmentation. The idea is quite simple. It says if this tissue is class 1, it's more likely than not that neighboring tissues will also be class 1. So if all your friends are in this boat, then you're probably in that boat too. And yeah, and then beta is a parameter that controls how much I promote this spatial coherence, how much I force a pixel to belong to the same group as its neighbors. And if I draw samples from this model, then I get things that might look like this. If beta is very small, I get very little spatial coherence, and as you let beta increase, you get more and more spatial coherence. And a question that we'll have to address at some point is how to choose beta, but we'll talk about that later. First, what neighborhood structure should I use? Well, in 2D, I'll go for a first-order neighborhood. In 2D, and in 3D, I'll take my 6 nearest neighbors in 3D. Would it be better to use a different neighborhood structure? Yes, but it's also computationally more expensive, whereas you do this, you can run everything in parallel by using a simple algorithmic trick that it's described in the papers. So we'll stick to this neighborhood structure. But as Daniel explained, it's not the best one. There's other ones that are better. And what about all the other parameters I don't know? Well, I don't know alpha, but I know it lives between 0 and 2. So I'll put a prior that says uniform between 0 and 2. So my prior knowledge is I have no idea, but all values between 0 and 2 seem like good candidates. And then for the gamma case, I'll use an inverse gamma prior, which is just some function that lives on the positive real numbers, which is what gamma k is, and it has some concentration around some values, and then it decays. And I'm going to choose alpha 1 and beta 1, alpha 0 equal to 1 and beta 0 equal to 1, such that this is quite flat. So it's going to authorize pretty much any value of gamma k that the data likes. And this is fine because I have a lot of data and gamma is not that large as a vector, so I expect that the data will find out what's a good value. And then I can summarize my Bayesian model in this way. And this Bayesian model is already a lot more complicated than the models we have seen so far. I have an observed data vector R, which is an image, an ultrasound scan image, and then I have labels Z that control what is the data fidelity term at each pixel value, and those data fidelity terms are indexed by 2 unknown vectors, alpha and gamma, and alpha, well, depends on a prior that lives between 0 and 2, and gamma depends on a prior that has 2 parameters, alpha naught and beta naught, and Z depends on 2 parameters, k that is fixed, and beta that is fixed for now, but we'll have to estimate at some point. So how will we do inference in this? Are we going to do any kind of optimization? No, optimization would be a very bad idea here. People try to do that, and they complain that the problem is NP hard, and what they don't realize is that an MCMC algorithm solves this very efficiently in a couple of minutes, where optimization gets stuck in local modes endlessly. So we're going to use an MCMC method. And we're going to, in particular, use something called a hybrid Gibbs sampler that I'll explain in a minute. So what we're going to do is we're going to draw lots of samples from this whole thing. So lots of samples. On each sample is going to have a set of labels that assigns each pixel or voxel to one class, and one set of values for alpha and one set of values for k. And we're going to run that and get lots of these samples. And then we're only going to look at the samples of z, and this will be equivalent to marginalizing, so getting just the distribution of z given the data. And once we have all these data points, it's easy to track a pixel and see if, I don't know, let's say 90% of the time, the model says that the label of this pixel is class 1, then we'll choose class 1. And if it says it's some other class, we'll go for the other class. So it's very easy to look at each pixel and see what is the class that appears most often. And this is the map estimator for that class, for that pixel. So that's what we are computing. We're doing an Rmax pixel per pixel. A Gibbs sampler is this MCMC algorithm, and what it does is address the model element by element in a sort of like divide and conquer strategy. So what you do is you generate your samples, but unlike yesterday where I generated my full vector, here you generate each element of the vector one step at a time, because it is possible to do this in a very efficient manner in this model. So what I do is first I scan all my pixels and I look at their labels, and I generate each one of these labels from this probability distribution. And this probability distribution, I will not go into the details, but it's just a probability distribution that counts how likely it is that you're class 1, class 2, class 3, class 4. And it's easy to compute that, because if you assume class 1, you have one data fidelity term, and you can see how much your neighbors look like class 1. So you have some functions, you compute their value, and you have your probability. Then you move to class 2, you have a new data fidelity term, and again, you just compute your functions, and you have your probability. You have to do that, and then you can very easily draw a random variable discrete from 1 to 4 with those probabilities. That's straightforward. And then for these ones, I'll have to do something a bit more complicated. But again, I'm going to look at each one of those unknown parameters, alpha k from 1 to capital K and gamma k, and draw it from its conditional distribution, the distribution of alpha k when everyone else is fixed. So the plan is you start with some initial values for all your quantities, and then one at a time you update those values by drawing a random variable. So it feels a bit like doing optimization, where you just improve things in one direction at a time. But here, instead of doing an optimization step, I do an MCMC step. So I draw a random variable. But these are always scalar random variables, or discrete in dimension 1. So it's very cheap to do this. You scan this over and over again. And in many cases, it turns out that Zn doesn't depend on many of the other Zs. So these other sets disappear from the conditional, and what that means is you can take all those Zs and update them in parallel. So that's what we do. The algorithm updates everything in parallel in just 2 or 3 steps, and that's it. So this is the conditional distribution of the Zs. I will not describe it in detail, but it has this data fidelity term, and it has this term from the prior. Then you need to evaluate. You do it once, and that's it. And for alpha and beta, we're going to use a Metropolis Hastings step like the one we described yesterday. And again, I'm not interested in describing this in a lot of detail, but what I said yesterday was that Metropolis Hastings was a general strategy where you propose some way of updating your parameters, and then Metropolis Hastings will accept or reject to guarantee that you're targeting exactly the distribution that you want. So that's what we'll do. We'll have a Metropolis step that accepts or rejects what we're proposing so that it works. So for alpha, we're just doing a random walk. If I'm standing here, I will randomly propose a new value in my neighborhood, within 0 and 2, I will not go outside, but randomly in my neighborhood, just a Gaussian perturbation, and then I'll accept or reject if I like it or not. In dimension 1, that's absolutely enough. And I'll do the same for gamma. And in each case, I have to accept or reject with this ratio that looks a bit complicated, but your computer calculates it in a few milliseconds, and that's it. And yeah, one last comment is that when you have a data fidelity term like that looks too complicated, you can often do some kind of Taylor expansion. Here I did an asymptotic expansion around 0 and infinity. And once you do that, you can compute this very quickly. So even if you have a data fidelity term that looks a bit of a nightmare, you can, with a bit of effort, turn it into something you can evaluate. And then in this MCMC algorithm, I don't have gradients or proxies or anything, so there is no computational issue. You just evaluate a function, you jump in the neighborhood, you accept or reject, and you move forward. So how does that work? Well, it works quite well. This is a toy example. I'm assuming that my tissues, that are 3 tissues, and they have these shapes. And when I do an ultrasound scan, I assume that it looks like this. And then I recover my classes from the ultrasound scan without knowing any of the parameters of the model. So here I've used these 3 parameter values. So I have 2 components that are almost Gaussian and a component that is clearly not Gaussian, and these gammas, and I recover things correctly. And yeah, you can estimate the parameters correctly too. Okay. And now I apply it to real images. So I have a real image, and I have expert segmentation of the tumor. So they do what we call potatoids. So they will draw something that looks like a potato in 3D. And we hope that our segmentation will be similar to that. And here in green, I have the 2D description of the segmentation that the algorithm finds just for the tumor. And in red is another approach we developed using level sets with a modified Mumford-Shah model, like the one Daniel described on Monday. And this is a Mumford-Shah model that doesn't have a quadratic data fidelity term. It has a Riley term, so it's much better, but it still does really poorly because it's just the problem is very difficult. And we do this slide after slide, and we get very consistent and accurate segmentations. And the experts then go and re-examine this, and they feel they can trust this. In any case, they can trust it at least as much as the potato they usually draw. So this is doing the job automatically, and then it outputs a 3D reconstruction of the tumor. And they can use the 3D reconstruction of the tumor to plan surgery, decide how dangerous the tumor is, and so forth. Okay, and I'll conclude my talk by discussing how to estimate the unknown parameter beta. And again, I'm not expecting you to retain the details of what the algorithm is doing exactly. What I wanted to illustrate in this talk was that another reason why Bayesian inference is interesting for imaging is that you can push a lot the boundaries of the models you can use. So if you're going to just solve things by optimization or by linear algebra, then you cannot get away with models that are very complicated. In Bayesian inference, at the expense of a bit of computation time, you can get away with models that are really, really complicated. And you can have lots of unknown parameters, and in one way or another, you can estimate all those unknown parameters. So that's an advantage. There's a trade-off. You are not as fast, but you can get a really accurate and reliable solution. So the last example is how to estimate beta. So beta is a difficult parameter to estimate. You can't just do a Metropolis Hastings thing, and I'll explain why. So this is the B-mode scan, just a slice in 2D, and different beta values give very different segmentation results. And okay, so we had chosen beta equal to 1, and the experts, I mean by we I mean the dermatologists have thought that beta equal to 1 was a good value, but first of all, they were not sure because it's not like we can actually know what's the ground truth. We tried to look at the lesion once we removed it, but it doesn't work because when you remove the tissue, the mechanical properties change, it shrinks, and then the shape changes. So you don't know. So that was one reason for estimating beta automatically, and the other reason was that I found it painfully frustrating that all the other parameters were inferred by the model, and this one was not. And at the time, I really wanted to estimate this automatically too, for intellectual reasons. So I changed the model, and I said, well, beta is unknown, and it has a prior. And the prior says just that beta lives between 0 and some maximum parameter value. We know that if this was, I don't know, like 2 or 3, that would be too high. So it has some value, maximum. And let's estimate beta jointly with a model. My Bayesian stats textbook said this was absolutely fine. You can incorporate beta into the model. Now you have a posterior that also involves beta. And you can marginalize with respect to beta. And now you have a model that doesn't depend on beta. So this should be fine. But computationally, it was difficult because when you want to do a Metropolis Hastings step or something like that, you have to compute this ratio. And when you try to compute this ratio, you end up with this term in your ratio, which is the ratio of the normalizing constants of the prior. So this is the C beta, and it's just as difficult as the C theta that we described half an hour ago. But it is, it has the additional difficulty that now the integral is over a discrete space that is very large. So this is clearly a nightmare to compute. Right? This is a space, a discrete space of dimension k to the power 9 million or something like that. So yeah, no hope. So first I thought there was no hope of estimating this, but then I realized that statisticians had started working on this problem. So we found different methods and we tried them. And the whole point was, how can you do Metropolis Hastings when you don't know this quantity? And we found one way of doing it, which is called likelihood-free sampling. So the whole point is you cannot write your data fidelity term. Your data fidelity term is just so complicated that you can't evaluate it. It's just beyond what you can compute. And the strategy is you replace computing this by drawing a random variable and getting an estimate. So it's similar to what we did to estimate the realization parameter yesterday. We wanted to compute an expectation. We couldn't, so we draw a random sample, and then we use that to just have an algorithm that doesn't evaluate things. So the philosophy is similar. Here what we have to do is draw a new sample from the prior, and then use that sample to compute a function eta, that is just the potential of the Potts function, because this is the function we're integrating to get C of beta. And here, instead of integrating that function, I'll just compute it. But because omega comes from the prior, I'm more or less getting an estimate of this thing I wanted to compute, of this integral. And so now we do another kind of MCMC algorithm. The philosophy is the same. We propose a new value and we accept and reject, but we cannot accept and reject with an explicit ratio. We have to use a ratio that is computed with the help of this auxiliary random variable from the prior, and this allows you to do the model. So don't pay attention to this. Just remember that if you have a problem that is really difficult and where things seem to not be working with the data fidelity terms that you have and with the algorithms that you have, or if you have things like discrete random variables or a mix of discrete and continuous random variables, or terms that you just can't evaluate because they are too complicated and involve integrals, then maybe a Bayesian solution could work really well because there's a full toolbox of techniques to address with these models that arise very often in genetics and history and epidemiology and things like that. Okay, so yeah, we do that. Again, my different parameters, and the one that the model finds is 1.02. So the model really likes beta equal 1.02, so that's very similar to beta equal 1 that the dermatologist also liked. So we were happy. And that's the end. I'll conclude by saying that, again, I really feel that we need a paradigm shift in imaging, and that the Bayesian framework can support this paradigm shift in different ways: uncertainty quantification, more complicated models, model selection, models with unknown parameters, and probably many other ideas that I have not yet postulated. In part 2, we talked about MCMC algorithms for problems that you can already solve with maximum-a-posteriori estimation. In part 3, we talked about quite clever approximations to the same inferences, and now the key idea was you didn't need to use MCMC sampling. And we also talked a bit about theory to support inference just by convex optimization. And that led to algorithms that were really fast. And in this last part, what I tried to say is that regardless of how long it's going to take you to compute a solution, many problems are just intrinsically difficult, and it's not a matter of computing a solution fast, it's a matter of computing a reliable solution in any reasonable computing time. And in that case, you can build very complicated Bayesian models that really capture lots of fine, subtle details of your problem, and you will invariably have lots of parameters you don't know how to set in addition to the one you care about. But by using MCMC algorithms, you can estimate all of them. If you become too ambitious, then eventually you'll start getting bad estimates of your model, but you can estimate them nonetheless. And yeah, so in this specific case of ultrasound imaging, we had lots of problems. We had several different data fidelity terms for each pixel that we could use depending on what tissue the pixel was. We didn't know the tissue, so we had to entertain all models simultaneously for each individual pixel. The parameters of the models were unknown, so we said, well, we'll estimate them. To estimate them, we need to use spatial coherence. And the amount of spatial coherence was also a factor we had to calibrate. And then we asked the model to estimate this as well automatically from the model, and it did that successfully. And if I had had a bit more time, I would have talked about how to actually estimate the number of classes that you have in your model, but I thought that was taking it a bit too far, so I stopped here. Okay, thank you very much, and we have 10 minutes for questions. Thank you.
You have 10 minutes.
No one is sitting until we get some questions.
It's because of the camera.
In your model for the field, at the very beginning of, you have this function p, and you have some tau I.
Yeah, the shape of the pulse.
Yeah, at the very beginning. Yes.
Yeah.
Here, yeah. And what do you know exactly about the tau I? Like it's a Poisson process, or
so
you have some independence between the.
I'm assuming at least weak dependence, and what I'm, mainly what I know is that P is upper bounded by some constant that I'll decide it's like 1, because any other value can be absorbed by AI. And I'm assuming that, so this looks like an oscillation function, and once I put the random tau I in here, I'm assuming that what I get out here is a uniform random variable between -1 and +1 or something like that.
Okay.
So that in itself is not very important, in the sense that it won't be important for the other conclusions. We know that there's no hope of recovering the tau I.
And you have some independence between when I are different? Or?
Yes, I'm assuming that from one voxel to the next, there is independence.
Okay.
Yeah. So because this is all happening just for pixel n. So the idea is inside just one pixel, there's millions of things that are scattering ultrasound signals. And yeah, and I'm assuming that when you move to the next region, those things are decorrelated from the previous ones. Yeah.
Okay.
Did this question inspire someone for another question? No? Okay, then thank you again.
Thank you.